Hello and welcome to the session. In today's session, we will be discussing about a very important design step which we perform in relational database management system, that is called normalization. However, we will restrict our discussion till third normal form only, and we will focus on how functional dependencies can be used to create or to do normalization. However, our approach in this particular session is going to be example oriented so that you can appreciate this particular example as well as the process of normalization, and then can study your course material and apply it onto a real database situation. So for the example, let us look into a student's database, right? So when we are talking about a student database, normally these are the things which we refer to, that a student has enrollment number, student has a name, address, and we have clubbed address into one field only, although there can be multiple fields as far as address is concerned. Then a student will enroll for some particular course, and that course will have some name, right? So these names are given for that particular course, and that course will be taught by an instructor, right? So there is an instructor for the course, and obviously that instructor will be having some office phone number. Okay, so all this information is recorded in this particular table, and what you can see is that the information which is shown in red color as well as in green color, both these information are redundant in nature. What do we mean by redundant in nature? For example, the information that 050112345, right? The name of this student is Rohan, and he resides in some place in Ranchi, right? Okay, so now this particular information is repeated in these three tuples, okay? This first tuple, second tuple, and third tuple. So there is a repetition of information, and same is the case with the instructor. This particular instructor, her room number is 103. That particular information is getting repeated, and the purpose of good database design is to minimize this particular content. So now why we want to minimize this kind of redundancy within the data? Well, there are three main reasons, and they are called the update anomaly, insertion anomaly, and deletion anomaly. Now, if we can define them further, an update anomaly is the one which occurs due to updating the table where the redundant information is available. For example, suppose that particular student Rohan changes the address to now Delhi, right? And by chance you made that, since the information is repeated at three different places, but we did not realize it, and we updated the information at only one place. So you can see that the redundancy of information has led to inconsistent information availability now. Okay, now over here it is Delhi and over here it is Ranchi. So there is going to be some problem when we access this particular tuple, right? And similarly, the similar thing can happen as far as this is concerned. Suppose the room number changes to 104, right? Then that particular problem is going to be, we have changed it at one place. We need to change it at all the places, which once again is a problem. So this is called the update anomaly. The second kind of anomaly is the insertion anomaly. Now, insertion anomaly is, suppose a new student joins, right? So a new student joins, and he or she is being given some different enrollment number and have a name, let's say Mohan, okay, and his or her his address is, let's say, in Mumbai, right? So that particular information cannot be entered in this particular relation, because the primary key to this particular relation is going to be the enrollment number as well as the course number, okay? Because a student can take, over here the student enrollment number is repeated, but for different course, right? So that is why there is a composite primary key, which includes enrollment number as well as the course number. So now this particular student's information cannot be entered in this particular relation because the primary key value is not known, in which course he or she has registered so far is not known. So we cannot enter this particular information. Now this is called the insertion anomaly. So this is a bad design. Insertion anomaly is primarily due to the reason we have a bad design. So what we are going to do with that bad design? But before we go to that particular situation, let us learn about one more anomaly, which is called deletion anomaly. Now deletion anomaly is, suppose we this Rohan drops the course MCS 201, right? Obviously this whole record will be deleted, this whole tuple will be deleted, and the information that MCS 201, the name of this particular course is problem solution and being taught by an instructor, whatever the name is appearing here, Nayan Kumar, who sits in 102 room, this complete information will be also getting deleted. It is no more existing in the table, right? So this is a deletion anomaly. So these type of problems do occur whenever we design a bad database. A bad database is the one which promotes redundancy, where redundancies are possible. So how we are going to eliminate that particular thing? Well, the concept which we use to eliminate redundancy and come up with good database design is called use of functional dependency. Y is functionally dependent on X between two sets of attributes and X and Y. Remember what we have said, two sets of attributes. X and Y are two sets of attributes which specify a constraint on possible tuples that can form a relational state of A. So that is the technical definition. And slightly lenient definition is considered any two tuples of relation A, say T1 and T2, and FD is said to exist between two sets of attributes and X and Y if the following holds in A. That is, if T1x and T2x agree, that means the value in these two tuples is same for X attribute, then the value of Y attributes also should match in the tuple. So it means that if tuple T1 and T2 have the same values for attribute X, then to hold X functionally determines Y on A, T1 and T2 must have the same value for attribute Y also. So this is the theoretical definition. But what it means, technically if we see, what functionally determination means in this dependency means that, for example, enrollment number 2345 last digits, right? Okay, this, three places this particular enrollment number exists, and in all the places the student name happens to be Rohan. Okay, all the places as a consistent name has to be Rohan. That means the enrollment number attribute can functionally determine student name as well as student address. They are also the same, right? So this is what we can say. So there is going to be definite functional dependency from enrollment number to student name as well as student address. Similarly, course name is functionally dependent on course number. Okay, so is the instructor also is dependent on course number, and so is the office. Office may not be dependent on the course number, but office may be dependent on the name of the course instructor, right? So like that we can define the functional dependencies. So functional dependency is technically defining the constraint. So how do we represent these functional dependencies? And we represent them with the help of a diagram. So this is the dependency diagram, what you see on, right? So what we have, the key attributes, what we had the key attribute, the enrollment number and the course number. So these are our key attributes, and the student number or the enrollment number is determining the student name, as I explained to you, and so is the student address, and course number is determining the course name as well as course instructor. However, the course instructor is determining the in office, that is the telephone number of the office of the that particular person. So this particular dependency diagram is a very important step in solving the problem, this particular problem, right? So let us now define the normal forms. So far we have discussed about the dependencies. Now let us define the normal form. So the first normal form, basically, which we represent as 1NF, we call as 1NF, is a relational table R is said to be in 1NF if every attribute of R takes atomic values. In other words, the following condition holds in R. There are no duplicate rows or tuples in the relation. Each data value stored in the relation is single valued, and entries in the column attributes are of the same kind. So if we take these three values, so this particular instance satisfies the conditions. Why? Because all the values, for example, these two values are different because first tuple and second tuple are different. Why? Because they differ in course number as well as, right? So they differ in course number. So accordingly, the entire tuple is not the same, right? And in addition, they are all atomic values. We are assuming these as atomic value, the address as atomic values, right? So everything looks to be all right, single valued, and the values are the same. For example, this contains course name, this contains the course code. Okay, so this particular relation is in first normal form. So we don't have to do anything else, but the relation is in first normal form, right? And what we see in this relation, there are a lot of redundancy related problems. What are redundancy related problems? Let me repeat: the update anomaly, the insertion anomaly, and the deletion anomaly. So all three problems exist. So what should we do now? Obviously, we would like to do or convert it to next normal form, and that is called the second normal form. Alright, so the second normal form is that student relation is in 1NF, yet it suffers from all anomalies. Therefore, a second normal form may be defined to overcome the anomalies. A relation is said to be in second normal form, 2NF we call it, if it fulfills the following criteria, assuming that the relation has only one candidate key. This is what we are assuming, which is selected as the primary key of the relation. So we have seen in the dependency diagram the key attributes, right? So let us try to once again look into the definition. The relation fulfills the criteria of first normal form, which it already does, that particular relation already does, and all those attributes that are not part of any primary key are fully functionally dependent on the primary key. So non-primary key attributes should be fully functionally dependent on the primary key. So let's look into the diagram, the dependency diagram. What do we see? This is the primary key attributes, right? Or the key attributes. This is just one primary key. Okay. However, these two attributes are not fully functionally dependent on the primary key, right? Fully functionally dependent on the primary key means that student enrollment number and course information together, course number, right, should determine student name and the student address. But that is not the case. Only student enrollment number can determine student name. Only student number can determine the student address, right? We don't require the course number for this particular functional dependence, right? So is the case that course number can clearly define the course name. This course instructor name is dependent on the course number itself. Okay, so the diagram clearly shows that there is no particular dependency, like no fully functionally dependent dependency in this particular case. So what should we do? Right? As far as this particular dependency is concerned, it is course number to course instructor and course instructor to course in office. So obviously there is a dependency which is called transitive dependency from course number to in office. So that way we will be getting the dependency as far as this particular diagram is concerned. Okay, so we have these kinds of dependencies. Let's represent these dependencies with the help of how we mathematically what we say, or the way it is to be represented. So student enrollment number determines student name and student address. Course number determines course number, name and course instructor, and course instructor determines course in office. In turn, because of these two dependencies, right? Okay, these two dependencies which are transitive dependency, what we can say, course number is determining course name, course instructor as well as in office. Okay, so the next thing is we would like to decompose, and decomposition cannot be at random. Decomposition has to be based on these functional dependencies which I showed you in the diagram, as well as the way the way we represent the functional dependencies. So look into the first dependency, how we are going to decompose this whole relation. Okay, so the first dependency we take, so what is the left side? This. What is the right side? Name as well as address. So the first relation will consist of student enrollment number, student name and student address. Okay, so that's what you see. Okay, this particular relation is because of this first dependency. Then the second dependency in this particular case is 2a. So we will take 2a because 2NF is slightly less restrictive. Okay, so we take 2a, and with the help of 2a, what we have? Course number, course name, course instructor and in office. So they form this particular second relation: course number, course name, course instructor and in office. However, there is an important thing what we need to understand. The primary key of this particular relation was student enrollment number and course number, and they are not appearing in both the tables together, right? So we require a third table, student enrollment number and course number table, which will form part of the decomposed relation. Otherwise, using these two tables, you cannot reconstruct the original table. What I mean is, it is basically slightly difficult to understand, therefore example is needed. So let's look into the example. Okay, so our example we break into three now, right? Three tables. So first table was, now you can see this red, whatever name of the student which is appearing in red happens to be appearing in three different places in the initial table, right? Now it is appearing because of normalization is decomposition, right? So decomposing the table we get, okay, just two tuples because there were only two students' data, Rohan as well as Aparna. All right. As far as courses are concerned, there were three courses, right? So 201, 202 and 203 operating system, which was being taught by Preeti Anand. So now the redundancy in this particular case also has been reduced. All right. But this third table is needed if you really need to reconstruct the original table. Otherwise, you will lose the data. Right? So the third table is very, very important. Why this third table is very, very important? You look into this, that the enrollment number, okay, enrollment number and the course register. Now it is no more redundant. Why it is no more redundant? Because the student enrollment number as well as course number together now forms the primary key. Together they are the primary key, not alone. So since together they are primary key, so it is not the redundant data in that particular sense. Now look into one particular thing. If I want to produce the original data, I'll be joining this table with this table and this table with this table. These two tables will be joined on enrollment number. These two tables will be joined on to the course code. So what you will get? 001, Rohan, the address, then MCS 201, problem solution, Nayan Kumar 102, which was the original tuple. So you will get back all the original tuples by using these three tables, and that is why it is no loss, non-loss decomposition, right? So this is very, very important, that the third table is very, very important when you do the normalization into 2NF. Now, once you have done the normalization in 2NF, then can we convert? Is there any problem? Well, in the student table, there was no such problem, but probably in course table and the student enrollment or the course enrollment, there was no such problem. But there is a third table in which we had a partial dependency, right, or a transitive dependency. So there may be some problem. So let us look into that instance. Okay. So this is where we had the course number, course name, and course instructor, and in office is available. Now what happens that this teacher Preeti decides to take another course 206. Now once again you can see this green area is redundant. All right, the redundancy is still there. So that means even though we have broken this particular table into 2NF, right? So it is already in 2NF, yet this table has redundancy. Okay, and whenever the redundancy is there, because of redundancy, you encounter the update anomaly, the insertion anomaly, and deletion anomaly, right? So that particular information is always there. So what should we do? Well, the situation is that the course number uniquely determines course name and course instructor, and course instructor determines in office, which was a transitive dependency. So what we really need to do, we keep one table as course number, course name, and course instructor. Okay, in this particular case, we don't need to add the third table because course instructor becomes the part of second table, right? So course instructor, comma, in office becomes the next table. So if we want to decompose this table, we can simply break this particular table into 3NF table with the help of these two functional dependencies. So course number, course name, and course instructor. So this is in 3NF. Similarly, course instructor and in office. Now what you can see here, once again the anomalies or the problems due to redundancy has been reduced drastically. Okay, and now Preeti Anand is appearing only in one place in the overall table, in this particular table, and you can join once again these two table. How you will be joining these two table? On course instructor. So when you join these two table on course instructor, the course number will be appended and you will get the original table without any difficulty. So this is once again not a non-loss decomposition, right? So your decomposition is perfect. Okay, and now you are able to get a third normal form of the table. So the important thing what you really need to understand here is that we are decomposing the table. Okay, we are decomposing the table. When we decomposed from 1NF to 2NF, what we made sure that we have one table where attributes are such that we are able to join the tables together, right? And when we are breaking from second normal form to third normal form, there is already going to be one attribute which will be common in the two table if you are breaking it into two tables, which can be used to join the join back the original table. So it is very, very important that when you do the normalization, you are able to reconstruct the original data. So this is the non-loss decomposition which has been discussed in your blog in quite a detail. So I think with this we would like to like to summarize this particular session, and that is normalization is the process of decomposition of tables to reduce redundancy and related problems. What are the related problems as for when we are doing the normalization? The first problem is there is an update. Because of redundancy, we have problem of update anomaly. Then we have problem of insertion anomaly, and we have the problem of these are anomalies only, so they are problem by the name itself, and the deletion anomaly. Okay, the second key point which we covered was a functional dependency defines the relationship between two sets. So, given two sets, a functional dependency will define that if they agree onto the left hand side, right, two sets of attribute, then they will also agree towards the right hand side. Then only we will say that set X, right, functionally determines set Y. So it is very important that the information should be consistent. So this is a kind of constraint onto database management system available. Then FDs are to be used to decompose a relation till third normal form. And BCNF. The BCNF we have not discussed here, but even BCS, Boyce Codd normal form, is also a very important normalization step, which is from 3NF. But normally in the industry, till 3NF is, most of the things are done till 3NF. So that is why we have considered the decomposition till 3NF. However, BCNF is available in your course material and you can have a look at it in more details. So with this, I would like to end this particular session. Thanks for being with me.